So in this video, I want to give you a high-level overview of how we actually go about quantizing an array of values or a tensor down into lower than 8 bits, more specifically 2 and 4 bits. So since the hardware we are using in Colab doesn't support storing numbers in RAM or in memory that are lower than 8-bit precision, we have to use what are called packing algorithms and unpacking algorithms to make this happen. So we have to literally quantize our values down into 2 or 4 bits and then pack them in to 8 bits. And so they're not stored as 2 or 4 bits, they're stored as 8-bit integers, but they're only using a portion of those 8 bits. And you'll see what I'm talking about in a second. For the sake of simplicity, I just want to make note that we will be using unsigned 2, 4, and 8-bit numbers in this quantization just to make the math a little bit easier, and we won't have to worry about the signed portion of the bit array. So I said we have to pack the numbers into these 8-bit integers, so these 8-bit arrays. And so what do I mean by that? So if we look over here, if we have our original array, remember the very simple array or tensor that we started with that was only a 1 by 4, we have the number -500, 0, 1, and 300. We have these numbers in the array, and they're all in 32-bit precision. The goal is to get them down into 4-bit precision, but we cannot store them as 4-bit numbers in our computer. The lowest that we can do is 8-bit. So what we do is we first quantize them down into a range that is supported by unsigned int4. And so we're going to constrain these into a range that's between 0 and 15. Now, when we constrain them down into a range that's supported by unsigned int4, the numbers themselves, although a 4-bit array could represent these numbers, they won't be stored in a 4-bit array in the computer because the computer does not support that, or at least our hardware that we're using in this course does not support that. And so 0 or 9 or 11 or 15 will each be represented by an 8-bit array or an 8-bit integer. And so what will happen is that a portion of those bits in each of these arrays will not be used because they'll be because we'll be able to represent them using only 4 out of the 8 bits. And so once we have quantized them down into this range, we'll have 0 and 9 here. What we'll do is we'll take these two numbers and then we'll pack them into an 8-bit array and it'll represent an 8-bit integer, but the number that it will represent will be different, right? It'll be 144 in this case. And then we'll take the 4 bits here and the 4 bits here on 11 and 15 and pack them into one 8-bit integer, 8-bit array, and then it'll represent 251. So I want to stop real quick and explain this whole packing step, because if you understand the packing step, the unpacking step going in the reverse is a lot simpler to understand. Okay, so I drew this up in a Miro board, and I want to start over here. So this is what I mean by packing. And if you remember in our slide, we represented our numbers as 0, 9, 11, and 15. Remember, we quantized them down into this range that could be supported by a unsigned 4-bit integer. And I said that we can't store them as 4 bits, right? Even though we could represent them in 4 bits, with only 4 bits, we can't store them in 4 bits. They have to be stored in 8 bits because that's the lowest our hardware can support. Well, in that case, we have 0 here. If I wanted to represent 0, the bit representation for 0 using only 8 bits is just all zeros. And 9, I can represent 9 with using only 4 bits. I only have to use 4 bits for each one of these numbers, but I'm kind of stuck with representing them using a full 8-bit array. I can represent 9 by this number right here, by these bits right here, 1, 0, 0, 1. I can represent 11 using 1, 0, 1, 1, and 15 using 1, 1, 1, 1. And so why is this? Well, if you look at how we read bits right to left. This 1 is in the first slot. That's going to be the 2 to the 0 slot, which 2 to the 0, if we turn that bit on, is only equal to 1. And then we have 2 to the 1 here, that slot's 0, so it's turned off. 2 to the 2 here, that slot's 0, so it's turned off. And then 2 to the 3 here is actually turned on. And so 2 to the 3 is going to be 8. So we have this slot for 2 to the 3, which is equal to 8 turned on. And then we add to it this slot, which is turned on for 2 to the 0, which is equal to 1. And then 8 plus 1 is equal to 9. And that's just a review on how we can read bit arrays. But we have all this wasted space because we don't need these bits to represent these numbers. So if we look at 0 and 9, what we're going to do is I'm going to first take 0 and pack it into this 8-bit array. I'm going to take these 4 zeros right here that represent 0, and I'm going to move them over here, and I'm going to pack them right here. And I'm going to take these bits right here, 1, 0, 0, 1, and I'm going to take them and I'm going to put them right here, and I'm going to pack them into this spot. And so that's what I mean by packing. And now what we're left with is we are left with this 8-bit array with these two numbers packed in here. And if we were to read this in bit notation, the 2 to the 4 spot is turned on, and then the 2 to the 5th, 6th, 2 to the 7th spot is turned on. So 2 to the 7th plus 2 to the 4th is going to give you, you can do the math in your browser, Google has a nice calculator, it's going to give you 144. This is the 8-bit representation for the number 144. And so that is why we represent it as 144. And then 144 is then going to be stored in this final array right here. And then, I'll move over a little bit so you can see that array. We're going to do the same thing with 251, and then 251 is going to be stored right here in this array as well. And so what we're going to start with, right, is we're going to start with our regular numbers, negative 500, 0, 100, and 300. We're going to quantize them down into these numbers right here, which are numbers that can be represented with an unsigned int4 array. And then we're going to pack each of them, pack each pair of them right here into an 8-bit array. That's going to represent a completely different number. And then that number is then going to be stored in another array here. And so that is how we do packing. Why does this work? Well, we are still, we're taking 4 numbers, right? And if we want to use 4 bits per number, that's going to be 16 bits in total that we need to represent these 4 numbers. Well, here we're representing these 2 numbers with 8 bits each. We know we need to compress this down to only represent these numbers with 16 bits. We have these 2 numbers that represent these 4 numbers, and they each have 8 bits each. And so here we have 8 bits here and then 8 bits here, so 16 bits in total to represent all these numbers. And so this is the packing step. Now the unpacking step is going in the reverse. So we have these numbers that are 144 and 251. We're going to unpack them into 0 and 9, and then 251 is going to be unpacked into 11 and 15. And then using the scale and 0 point, because we're going to use asymmetric for this, we're going to, and why are we going to use asymmetric? Because remember, in symmetric, we have to not only assume that the unquantized range is from the maximum number to the negative, is from the negative of the maximum absolute value number to the positive of that absolute value number. And so we have to do the same thing with the quantized range. If that was the case, we would have the quantized range being 15 here, and then the minimum be negative 15. But you know, uint4 doesn't support any negative numbers, and so we're not going to do symmetric for that reason. We're going to use asymmetric. But essentially, the unpacking step is in reverse. We are going to unpack them first, back up to the uint4 range, and then we're going to use our scale and 0 point to scale these down here into uint4 to scale them back up into the unquantized range to dequantize our numbers. And that is how we are going to represent our numbers using 2 to 4 bits per number.